Waves are disturbances that carry energy from one place to another. There are many different types of waves. For example, slinky waves. Sound waves. Water waves.
That's not me, by the way. That's me. Finally. And seismic waves, the waves generated by earthquakes.
We've got windows and everything have fallen out.
Highway Patrol emergency.
Cypress section of the West Grand Freeway has come down.
The Cypress structure has collapsed. 50-foot section.
All of these waves are called mechanical waves because they need what's called a medium to travel through. In a slinky wave, for example, the slinky is the medium. The movement of one coil makes the next one move, which makes the next one move, and so on. This basic process occurs in all mechanical waves. When each coil moves perpendicular to the direction of the wave is called a transverse wave. Each loop is moving only up and down as the wave moves from left to right. You can see that the blue tape on one of the coils does more or less the same thing. The waves move sideways, but each particle moves only up and down. One of Microsoft PowerPoint's animations is called Wave, and it creates a transverse wave by moving each letter up and down. When each coil moves side to side in the same direction that the wave is traveling in, the wave is called a longitudinal wave. Each loop is moving first to the right and then to the left as the wave moves from left to right. Sound waves are longitudinal waves. Electromagnetic waves are different from all other types of waves in that they don't need a medium to travel through. The light coming from the sun, for example, can get to us here on Earth even though the space between the Earth and the sun is a vacuum. Light doesn't need a medium because it's a self-contained wave of electrical and magnetic energy. We can represent a wave with a simple diagram. We'll use a transverse wave because it's so much easier to picture. Most waves in nature have a positive and a negative component. The top of the wave is called a crest, while the bottom of the wave is called a trough. The so-called wavelength of a wave is the distance from one crest to the next, or from one trough to the next. This distance is also the wavelength. Wavelength is usually measured in meters. The Greek letter lambda, which is the Greek letter L, is used as the symbol for wavelength. So, if the wavelength was 2 meters, I would label this diagram by writing lambda equals 2 meters, but I would read this as wavelength equals 2 meters. A wave's amplitude is the height of the crest of the wave, or if you like, the depth of the trough. This wave has an amplitude of about 40 centimeters. When two waves meet, they pass straight through each other. Here, a larger amplitude wave pulse moving towards the right meets a smaller amplitude wave pulse moving towards the left. After they pass through each other, the larger wave pulse is still moving towards the right, and the smaller wave pulse continues moving towards the left.
If waves didn't pass through each other, then, for example, all the light reflecting off me towards the camera would crash into all the light reflecting off the camera towards me. The light waves would bounce off each other and scatter in every direction. All we would see is a blur of light.
At the point where the waves meet, the amplitudes of the waves add up. This is called superposition. This amplitude plus this amplitude equals this amplitude when the two waves superimpose. If the wave pulses are on the opposite side of the slinky, the waves superimpose to temporarily reduce in overall amplitude before moving on. Frequency, given the symbol f, is the number of complete wavelengths that pass a given point per second. It's measured in hertz. The frequency of the top wave is 1 hertz. One complete wavelength is being produced per second, while the frequency of the bottom wave is 2 hertz.
Here, I've attached this signal generator to this speaker.
I've set the output to 1 hertz, so the speaker is vibrating once per second. I can increase the frequency to 2 hertz, that is 2 vibrations per second, and then to 3 hertz, 4 hertz, and so on. Humans can hear sounds only if they're above about 20 hertz. This is 60 hertz, 90 hertz, 400 hertz, 800 hertz, and about 9,000 hertz. Humans can hear only up to about 20,000 hertz. My ears are starting to hurt. Thanks for watching this short excerpt from Shedding Light on Electromagnetic Waves, the 6th program in the Shedding Light on Light series of programs aimed at high school students studying the topic of light. The program begins with an introduction to electromagnetic waves, how electricity and magnetism are related, how James Clerk Maxwell came up with the idea of an electromagnetic wave, how Heinrich Hertz actually proved their existence, and how Guglielmo Marconi started using radio waves in long-range communications. We then look at waves in general. We look at transverse waves and longitudinal waves, wavelength, frequency, and wave speed. The rest of the video looks specifically at electromagnetic waves, radio waves and microwaves, infrared light, including thermal imaging and night vision, visible light, including lasers and colour, ultraviolet light and how it can cause damage to unprotected skin cells, X-rays, including radiography and radiotherapy, and finally, gamma rays and how they are used in industry. Visit our website to get details about how you can watch the whole program and to download the worksheet. In fact, worksheets from every Shedding Light program can be downloaded from the website, and there's a whole bunch of practical activities that you can download as well. Thanks again for watching.